Alright, another draft physics video presentation. Just piling on at this point, but what am I going to do? I can only provide the reasoning, and if people just can't accept the truth, that's what it is. And that's sort of what there's an indication of. I mean, it really should by now have triggered people who actually care about the truth, and they'd say, hey, he's got a point, all of physics is based on this experiment, and here they've been explaining it and telling us it's way complicated and all this mystery stuff is happening, and frankly you can pick it apart and analyze it and figure out, oh, it's so obvious what's happening and it's so simple, and it's just pathetic, really. But anyway, AB science, those types, just terrible, despicable cowards. They just won't accept the truth. The truth has been shown to them. They just don't want to accept it. They want to keep their little wooey physics, because I've really blown up. There's no cement anymore. It's just the whole thing is dissolving, and because this is everything to their whole theory. All of quantum mechanics is dependent on this experiment being what they say it is. This is Heisenberg, this is entanglement, this is superposition. All of it is based on this experiment. And if this falls apart, it all falls apart. And they're just cowards. They can't accept the truth that they've been, propagandizing a silly religion. Yeah, they've been devoted little servants to their to a god made up in Bohr's little brain. Alright, anyway, so this is an excellent demo, physics demos it's called. Some of their videos might be worth playing eventually, not too many views for which, this is just such a pretty, two-slit experiment. And he has the dimensions in it, and that sort of just gives it all away, and I could just show you how simple it is, mathematically. And so we'll play the demo, but really just for the images. It doesn't, these demos don't say anything about theory, so.
This is a demonstration of the pattern you get when you send light through two slits. In this demonstration, I've got a laser here. I'm sending it through two slits that are separated in the first case by 0.25 millimeters. And then second case by 0.5 millimeters, larger separation. In both cases, each of the two slits is 0.04 millimeters wide.
So they're very small. 0.04 is 80 wavelengths, though. So let's understand, even 0.04 millimeters, which sounds small, which in most cases is small, still isn't small enough in the sense of creating a really big, wide envelope pattern. It's still 80 bars worth going just one way, so it's 160 in the whole 180 degrees. And that's the smallest dimension, and that's the key point here. It's the smallest dimension. The smallest distance between two surfaces, is going to be 0.04. And then the largest distance between two surfaces, is going to be 0.5 plus 2.04, so it would be 5.8. So 0.58 is the largest distance. So with those two numbers, you can predict the whole thing.
So what you see now is the pattern produced.
So that's just too pretty. I mean, I wish you could see it as well. I mean, it'd be nice if I could blow it up in some convenient way, but there's, it's a little dicey doing that. But maybe we'll give it a try. I'll pause and give it a shot. Well, now I'll have to shrink it again, which will be a pain in the ass. Anyway, really nice pattern, just really, very pretty. But the point is that you can really see in the pattern of the breaks here. Well, let's use the, whoops, it's not the thing I want to use. Yeah. What do I call my arrow? Yeah, there it is. See? Oh, excellent. Okay, so you have these dark spots here that are just so glaring, so obvious that they're there. This is really something going on here that needs to be accounted for, and conventional physics will not account for it. They can't explain why there's two patterns here at all. They just don't have any clue why that's happening, and they don't even try, in a sense, to explain it. And it's a byproduct of the fact that there are, in fact, 4 sources in the experiment. So maybe I just go to, and you can see that this middle one is twice the size. Then that should give them a giveaway too, that maybe they're not thinking about this right, because why is it doing that? And they don't really have an explanation. So I guess I'll explain it, right? There's no point in taking any time to do anything else, but just get to it. So I just want you to see the little bars are small. So the catch is, like if you do the math, like I said, 80. So there would be 80 of the, if you could go all the way, doing the whole 90 degrees, one side. The truth is if you divide the numbers, you just divide the wavelength of the light into the distance, which is 0.4 of the openings, that'll tell you there's going to be 80 bars going this way. And you can sort of see from this image, let's say this was 10 degrees of the image, you could sort of get the idea that that stretches out just right, or pretty close. You can almost figure out how many degrees you got here. So there'd be 80 of these big clumpy things, okay, so 80 of them per 90 degrees, so 160 across the whole pattern. And the little ones are going to be this is the 0.25 image, so this is where the bars are a little bigger, and it comes out to like 500. So there's like 500 of those going that dimension. So it'll be 1,000 this way. And you can sort of just do the math. You can just count. There's 7 of them here. 7 times 80. Oh, bingo. You got the 540 number or whatever it comes out to exactly. So you have 500 of the little bars per 90 degrees and 80 of the big clumps per 80. And that's how simple the math is. You just divide the wavelength into the smallest distance the experiment creates, and then take the biggest distance the experiment creates between a surface. And those two distances will tell you everything you need to know, and you're done. You can predict exactly how many bars there would be if you could see all of them. And obviously, why do they degrade? Why do they stop producing photons as you go further out? One, because you're projecting on a flat screen, which means you're spreading the photons out, which means they're less effective as photons. Second is because, this is being caused by an actual physical event. And the physical event doesn't happen as many times going further over. It's happening because of scatter. And electrons aren't scattered as much in those directions. All right. So, so I'll go to the drawing table and make it even more clear. But I mean, it's perfect. I guess I'll show you the small bars first, but there'll be no point in going back to that. By
this two-slit pattern. And you can see a big bright spot here, but I'm hoping you'll be able to see that there are small divisions, maybe 10 or 12 divisions within this big bright.
Well, you could actually figure it out because, it's actually either a little bit more or a little bit less than 2. So it's 7 in these nodes. There's 7. So it's 14 at a maximum, but it could be 12. Because, see, that's all created by the fact that the experiment is inside of 1 millimeter, right? A ½ millimeter, right? As I just pointed out, the furthest distance between two surfaces is 0.58 of a millimeter. That's how small the experiment is. And that experiment is being shot right to that center. So it's a very small place, and the two bands start that 0.58 away from each other. That's where this 90 degrees starts and this 90 degrees starts. They don't start at some zero in the middle. No, they both start where the center impediment is, essentially, and then go fan out. And so the starting point for the two is different, and they start, some portion have already been on. They don't start with a perfect 0. So anyway.
Spot. Those are produced by the fact that we have two slits, interference, both constructive interference and destructive interference through this region.
Right. Well, those are just words, and it's just nonsense. That doesn't work, frankly. You can't do that math and have it work. There's 4 surfaces, and this has nothing to do with waves going through openings. This has to do with crap hitting surfaces. And that's all it has to do with, and that's exactly what the math says, and that's exactly what the experiment's about. It's not a wave. It doesn't demonstrate. It's not nail in the coffin evidence that light is a wave. It's nail in the coffin evidence that light isn't a wave.
You can also see it divided out here in the other bright spots. So if we move to
the other
doubling
bright spots,
the separation to 0.5 millimeters.
There you see, it's just twice as small, right? So all you've done now is say, well, instead of 500 bars per 90 degrees, you have 1,000 per 90 degrees. Just do the math. Just do it's kind of easy with a 0.5 and you average 500 millimeter light. This is more like whatever, 390 because it's green. So it's a little more than 1,000. But that's all you need to do, to get the number, to get how many there are in a 9 degrees of transition, and that'll tell you exactly how big they are because you just do the times 1/2 pi. Done. All right. But you can just see they're so small that you can't see them, but they're half as big as they were before, but they're filling exactly the same spatial area essentially because you didn't change, the opening size. All right. So that's all we need for that. So off to the drawing board. All right, should be back without instant. All right, so the key is that there's different ways you can do this experiment, right? You can have the slit, the barrier, smaller than the opening, or you can have the barrier bigger than the openings. And depending on how you do it, you're going to sort of change how you have to understand what's really happening, and it'll just show you. It's the proof essentially of the experiment is the fact that you change those things, you change how the pattern looks. But what they're not really accounting for is the fact that this experiment, again, it's 0.5 of a millimeter, 0.58, this distance to this distance. So that's the furthest away two slits are from each other. That means those are the vectors that have the most probability of distortion, one line being much longer than the other line. And really, the other point to understand is it's really just about 2 different patterns, right? From those 2 points, you're going this way, and then from those 2 points, you end up going this way, the opposite direction. And the part to really understand is at this target, I could put the target out here maybe. I probably could put it further. This is still 1 millimeter here, This is still 0.58 of a millimeter, right? A tiny little place is where the straight light, the light that goes through and doesn't get bothered, is still hitting a tiny point, the center. That's why that center is so much brighter, is because there's a lot of light that just goes straight through. And what you have to understand is that the experiment starts for each one of these vectors, really. This is the 0, and this is the 0, of where you're going to start a pattern going this way, and where you're going to start a pattern going this way. And what you're really saying is that, how many times the wavelength goes into the number of nanometers, whether it goes in even or with a remainder. See, I could do the division. I could convert this into nanometers, and I'll get 58,000. And then I can divide it, by the light, which might be 364. All right, and the odds of me getting an even number, a whole number, I'm going to get like whatever. I'm going to get like well, let's make this 564, and so I'm going to get a number like 1082.7. This 0.7 is hugely important because that's basically telling you it's whether it's if it was 0.5, it would be exactly half a wavelength. So it's going to start here, not with a on, okay, it's going to start with an off, because that's 0.5. So this is going to be a dark, and it's not going to get light till it goes to here. And then this is going to be a dark, and it's not going to get light till it goes to here. And then you can understand all this wash light from the lasers going right through the middle, plus the fake node, which is in between the two. The light's going in the same way it's going out this direction, right? So those are the vectors. Well, I can't draw down there. Should know better. Yeah, that's breaking the rules. So when the light's coming off the two surfaces, any surfaces, it goes this way. But this is really the stuff creating the nodes, the stuff where both lines are going in the same direction. When both lines are heading towards each other, this is really a fake node in the middle. So you have a little tiny fake node right here in the middle, and that's filling in the gap between these two. So these two started like a 0.5 millimeter away from each other, right? And then there's another fake node created by the interior going opposite direction vectors. The vectors pointing towards each other instead of the vectors going, it's this simple. Look, these vectors are going both in the same direction. These vectors are not going in the same direction, right? So this is like a fake node here in the middle that's very small, and it's basically just filling in the gap between these two, and that's why it looks like a little more or a little less than two nodes in the middle. So that little bright spot in the middle is being created as an optical illusion. The real middle there is really an off. It's just you can't see it, because this fake node is plastered on top of it. So anyway, so that explains the big middle. And the rest of it is just this simple math. There's 4 point sources, and you can interpret them lots of ways. You can say, well, this vector and this vector, or this vector and this vector, or this, but there's still only 4 point sources. From every location, it's just saying, how much light am I getting that's in phase? So there's a line from each one of these points going to each location on this surface. There's a line, okay, 4 points. I can see the 4 point sources. So if I have an eyeball right here, I'll see 4 point sources shooting me light. And it won't be the open slit. No, it'll be the surfaces, the 4 surfaces. If I look the other way at this and I could see tiny, tiny sources, I would see it's the surfaces. The 4 surfaces are shooting me the photons. And all you really need is for 3 of those sources, right? Any 3 sources hit, there's light. So anytime 3 sources, 4 is even better, but 3 will do it. So as soon as I have 3 sources, I'm going to have light. If I have anything less than 3 sources, that is only these 2 sources, or these 2 sources, or this source and this source, if they're in phase, then no light. So less than 2, no light. Well, 2 or less, you're not going to get any. You're not going to see it as a on node. 3, you're going to see it as on, but it's not going to be as bright. And 4 will be brighter because now you have 4 sources, 4 extra pieces of parts, so you're much better off. And then you'll have the brightest spots. And that'll explain also why there's such a little bit of blurriness in some of this, is the fact that if you understand what's really going on is these two are basically projecting on exactly the same location. It's only 0.5 millimeters of difference in the 2 patterns. So if I was to close one of these slits, the pattern created by this slit and the pattern, and then close this one and then open this one, the 2 patterns would be almost right on top of each other. I wouldn't be able to tell the difference. It was such a tiny difference on this wall that's meters away, so I wouldn't be able to see the difference. And that's the key to understanding the experiment, that when they draw these 2 humps over here, that has nothing to do with the truth. The 2 slits don't make 2 humps a foot apart from each other. No, the 2 slits make 2 patterns almost right on top of each other, just barely a little bit different. That's why the brights are bigger than they should be, is because those two places where you can be in phase is a little fudgeable, you know, because of the tiny distance between the two patterns. And that little tiny difference means that it's creating places that work, more places than it would be, because it's essentially just blurring the image, blurring the true representation. So again, all you need to know to do this math is just find out, to know what the pattern's going to be, find the shortest distance between two surfaces, and that'll tell you how big the little bars will be, and it'll tell you exactly how many there are. Again, all you do is divide it. How many wavelengths fit in the distance? So you just did, this is 0.4, he said, 0.04. So that comes out to 4,000 nanometers. Then you just divide that by your wavelength. Let's say it's 360. And then you just multiply that by 1/2 of a pi to put it on this surface. And I'll tell you exactly how big they'll be on this surface. By just finding out what this number will be, will tell you how long this line is. And all you're really doing is putting this number on that line. It'll tell you how many nodes there are, and once you know how many nodes there are and what size line, you'll know exactly how big each one of the ons is. And now you just multiply it by 2 if you want 180 degrees worth. There. So that's it. That's all there is. You don't need any integrals. You don't need any of their wave equations. You don't need any of this fancy nonsense. It's dirt simple. You just count how many wavelengths fit in the distance. And again, so I just take the biggest distance, which was 0.58, and I do the same thing, and that'll tell me the little ones. So the big ones will be told by the smallest distance, the big envelope pattern. The smallest distance in the experiment tells you what those numbers are going to be. The biggest distance tells you how big the little bars are going to be. That's it. Dirt simple. And no room for waves in here anywhere. So let's just understand their theory doesn't work at all. I mean, first off, waves in these positions can't work. So I'll be playing another video of another physics video that's just completely wrong. They're selling it like it works when it doesn't. This theory won't work. This Young drawing doesn't produce the right, because the point sources are here and here. That's the wave center. They don't put that in the math. They put these real dimensions in the math. The distance between the slits. That's the stuff they put in the math. The surface distance. They don't put the wave center distance in the math. Clear deception, clear nonsense, clear shenanigans. But the point is, this doesn't work. It's clearly the surfaces. And no rational person would draw this and say, because that's the math that'll work. If I put those 4 waves in, that'll work. No rational person has a wave break in the middle of the opening. No rational person has a wave go through the surface. Right? No rational physicist. That doesn't work. Waves can't do that. This is obviously about scatter on surfaces. The surfaces create the whole phenomenon. They're the cause of the effect. Clearly, decisively, without reasonable doubt by any honest person. That's the facts. And they don't point to waves. They point overtly to a concept like scatter and overtly to something like, particle scatter. So, yeah, I've done my job. I don't think he says any more in this video, but I'll play it.
Then a wider separation means tighter spacing between those interference fringes.
Right, so the bigger the distance between any two sources, the smaller the smallest pattern is going to be. So that's all you're looking for, the biggest pattern and the smallest pattern, and you just equate it directly to the greatest distance between a surface and the smallest distance between two surfaces, two sources. The surfaces are sources. The single slit experiment is the two source experiment. The two surface, the two source experiment. That's what the math overtly says. Even their own math overtly says two sources. All right, and then the double slit is clearly the four surface, four source experiment.
So you may or may not be able to see on the screen now that this main maximum is still as wide as it was before, but there's double the number of individual divisions within it.
Exactly consistent with the theory that you've now doubled, essentially. Now, you didn't really absolutely double, right? Because it was 5 and 0.25. Those are the two numbers. And what you're really doing to the distance is you created 0.58, and then you create 0.33, which isn't an exact doubling. It's a little bit off. I mean, 5.8 isn't 66, is my point. 2.5 is 1/2 of 5, but 0.33 isn't half of 5.8. So it actually, if you can actually see it, there is a subtle difference. Again, proving my point.
So the actual pattern that you can see right now is the single slit diffraction pattern for a single slit with 0.04 millimeters.
Right, that would add up. And frankly, like I said, they're a 0.5 millimeters apart. The two single slit projections are only 0.5 of a millimeter apart. And in this case, yeah, this was the 0.5 image. That's it. So there's only 0.5 of a millimeter on this image that's probably a foot wide. So this image might be a foot wide on the screen, right? It's 5 inches anyway, let's say, or 6 inches. You're not going to see 0.5 of a millimeter difference between those two patterns. They've just shot right on top of each other.
And then the divisions within that pattern, which I think we'll be able to clearly see on this one, is the result of the double slit pattern.
So again, it's just about two numbers. It's just about how many wavelengths there are inside the distance, because obviously that's telling you how many times you have a possible vector difference. How many times it's possible to create a wavelength of difference in the length of the line. It's told to you clearly by how many wavelengths fit between the distance. That's what decides it. And so clearly, it's just about surfaces. All right, so we'll move on to a Khan Academy video. It's just so bad that, it's worth playing just because it's so bad, right? So this is what Bill Gates' money buys, is, crap physics, really. But it's all crap. I mean, like I said, the whole thing, right? Their entire monstrosity that they've created, this monstrosity of wooey bullshit, is all based on misinterpreting this one experiment. They screwed this one up, and then they screw all the rest of them up just the same, because they really just don't care about what the experiments really say. They just care about how they can convert them and pervert them into what they want them to say, like Stern-Gerlach. An experiment done on silver atoms, and they're telling you what the spin of an electron is. Too silly.
Young's double slit experiment looked a little something like this. You've got a barrier with two holes in it, but these holes are so small and so close together.
Why would they be so small, and why would they be so close together? So again, just something, you don't have to believe that. So again, this one's with a big barrier and small openings.
We characterize them as slits, and double because there's two of them.
Right, and the obvious other characterization is it's four sources, four surfaces, four places that something happens. And I'm just saying that was intuitive to me from the moment I saw it. That was what I saw was, well, if I was to blame something for the pattern, what could I blame? Well, I'm not going to blame this open middle stuff, because that doesn't seem like it's doing anything. And it seems the important feature is the surface. And that was sort of proven by Newton's original aperture experiments. what happens when you close an aperture? What happens to the light as you make the aperture smaller and smaller and smaller? Well, the odds of it being right next to a surface go way up. So the smaller I make the hole, the more likely it is you're going to be next to the hole when you go through the hole. You get it? If I make a big giant hole, you can jump right through it and be feet away from the edges, right? But if I make the hole really small, you're only going to be inches from the surface. The smaller I make the hole, the harder it is for you to miss the edges of it. So again, the indication was already there 300 years ago about what the rational explanation would be, that this has something to do with surfaces, that maybe surfaces have electrons on them, and maybe photons hit electrons, and maybe that's the simple answer.
Young was the English physicist who first did an experiment of this kind, and what we do nowadays is we take a laser.
So he wasn't the first. Newton did the two interior surfaces and then the two exterior surfaces, so he did the same concept. He just didn't put both of them together at the same time, but he certainly did the two ways you could have a surface, facing in and facing out.
We shine this laser at the double slit. Now the laser has to be wide enough.
So instead of drawing photons in some sort of rational way, like rays, especially a laser beam doesn't look like it's really doing all this crap. But anyway.
It hits both holes, and you might think, oh my god, you need a big laser. No, you make these holes very close together. That's why you make them really close together, or at least one reason. The other reason is the distance between these holes has to be comparable. Doesn't have to be the same size or smaller, but it has to be around. It can't be a trillion times bigger.
But it can be 80 times bigger, as the guy just a minute ago showed. So even though 80 times is really pretty small, nobody really does the experiment actually, with a slit that's 0.004. All right, so, that's an insanely small. A wavelength of light is an insanely small slit. So just understand, when they say this crap, they aren't really thinking about what they're saying. So when they say a slit smaller than or as small as the wavelength of the light, they don't even understand how actually small that is. It's an insanely small slit. It's really, it's, mere 1,000 atoms. Less than 1,000 atoms thick, wide.
Then the wavelength of this laser light you're sending in here, it's got to be around the same size or what?
Okay, so again, it doesn't have to be anywhere near it. It can be humongous, thousands. Okay, you can make this slit thousands of wavelengths wide, and you'll get lots and lots of pattern.
What we're going to talk about here, you won't see.
The only way they can make their math work is they have to make the slits infinitesimally, irrelevantly small. If they make them small enough, there's no relevant difference between the smallest distance and the biggest distance. That's the truth of it. They're just trying to kill the pattern, not trying to show you the pattern. They need to kill it because they can't explain the actual pattern. So they have to create a fake pattern to explain, one that isn't the usual pattern. One is the highly unusual pattern. That's the only one they can predict. Where I showed you pretty overtly, I can predict all the patterns.
See the interesting pattern that's going to emerge. You might wonder what I've drawn here. What is this? This isn't a wave. This is a wave right here. I thought these were waves. What are we doing now? Why we got this different
So again, he's got the silly illustration, sine wave nonsense. Clearly a frequency doesn't need to be a sine wave. Frequency of bullets isn't a sine wave.
Representation, and the reason is, when I draw this pretty much just lets me show a wave in one dimension. But that's not good enough. This process is going to be fundamentally two-dimensional. This wave's going to spread out in 2 dimensions. So I can't draw it like this, I have to draw it like this. Now this whole line here, what does this represent? This represents a peak. Everywhere along here is a peak of the wave. So you've got this wave filling up this entire region. These lines represent lines where...
So as I understand, all of this minutia, this baby talk about how waves work, they're like ocean wave. The math doesn't work for that. So it doesn't going to give you the right pattern. And clearly photons don't do what these kind of traditional waves do, which is they don't create a spot that blinks on and off. Okay, then it goes high and low. they create a spot that's permanently on and a spot that's permanently off. So it's not exactly like any kind of regular wave theory anyway. Even if you could break it and play this game that this is something about water waves, lights, moving through some medium or something. Even if you break it that way, you can't break it that way and still do any kind of rational drawing. Again, he's going to draw the waves exactly where the math says they aren't. So that's what he's going to do.
For every point along there is a peak of the wave. What's in the middle? Yep, in the middle would be the trough of the wave, or the valley. So that's what I'm going to use. I'm going to use this representation for the wave. This will let me show this wave spreading out in 2 dimensions better than this one could. I couldn't draw it very well with this one. So, what happens?
You're just drawing a frequency. That's all you're doing. You're just establishing a period of time between events. Whether the event is a trough or a peak is irrelevant. The only thing that matters is whether they're in phase or out of phase. And the fact is the only thing that matters is, are you going to put the photons broken by the scatter on the surfaces? The photons are broken into sub-pieces, composite pieces. And where do you put the composite pieces back together? And that's all that's going to be happening in this experiment. That's the reality. And even though I'm offering $1,500 to a meaningful physicist to debunk this, they won't take the money. They won't do it. They're running away.
This wave comes in here. This laser light comes in here. Well, that part hits that barrier. It doesn't get through. This part hits that barrier. It doesn't get through. This part hits the barrier. It doesn't get through. The only portion that's going to get through is basically this portion.
So, I mean, it's funny, right, that he says that, because obviously you do have to draw the wave way over there, and it has to go over the peak, right? Let me get my little arrow. It's not a very good arrow, but I mean, he just says, oh, look, the only portion that's going to get through is this. No, you actually, for the math to work, you're going to have your wave go right through the barrier there, and then you're going to have it do this weird thing where it's going to break right there in the middle. That's the math that works. Okay, so that's where you have to put your wave center. The center of your wave has to actually go right through the barrier. So even though he says, oh, that doesn't make any sense, that's what your theory says. That's what it predicts. Where was I? Well, play the video. Okay.
Here and this portion here. These are going to be the ones that make it through. And so what happens? What do you see on the wall over here? If this was a screen that you could project the light on, what would you see? Well, naively, what I would have thought, I've been like, okay, shoot, light comes through here, bright spot. Light comes through here, bright spot.
Right, and those bright spots would be 0.5 of a millimeter apart. And you wouldn't see the difference. It's so small a difference between those two dots. Obviously, the laser spreads the whole thing, so you know that at meters of distance, those dots are going to be blobs, and those blobs are only going to be one of them's going to be a little shifted, a little half millimeter shifted from the other one. You'll never even be able to see the difference. So, of course, they draw it wrong again. Always draw it wrong. Never understand the actual physics. Never understand that projecting on an infinite plane distorts the image. Don't even accept that simple piece of physics. I mean, you can understand how they really don't understand physics conceptually. They just understand it mathematically. And there's a huge difference.
You just get 2 bright spots, right? Well, no, that's not what you get. That's why this experiment is interesting, because you don't just get 2 bright spots. You get a pattern over here because
you have sources, 4 of them. And when you had a single slit, you get a pattern because you have 2 sources.
Waves don't just travel straight through this hole. When a wave encounters a hole or a corner, it spreads out, and that spreading out we call diffraction. So
again, and we know why water waves do it and sound waves do it, is because they slow down having to go across surfaces. That's not happening here. They don't have any theory that light does that. And again, it doesn't work anyway. The math doesn't work. So here he is drawing. Where is he drawing the wave center? Right in the middle of the slit. Where is the math say? The math says the surface. So again, just ignore their own mathematics and draw it completely inconsistent with their own mathematics.
You're going to get a wave spreading out from down here, so it's not going to go in a...
So when he starts drawing vector lines, the vector lines are going to have to be drawn from the distances of the surfaces from each other. That's where he's going to draw the vectors. So he's just going to ignore this drawing he's doing. This drawing is not predicting anything, okay? It's just distorting, and it's giving people false impressions, and that's all it's for. It's just a piece of propaganda.
Straight line, it spreads out in 2 dimensions. That's why I had to use this wave drawing representation. It's going to spread out from the top one too. Look what's going to happen. You're going to have 2 waves overlapping. These 2 waves are going to start overlapping, and where they overlap constructively, you'd get a bright spot. Where they overlap destructively, you'd get a dark spot. Where it's sort of half constructive, half destructive, you might get a mediumly bright spot. How do we figure out what's going to be?
So again, that doesn't happen either, any of this medium stuff. As you could see in the previous illustrations of the pattern, the little bars aren't getting gradually light and gradually dark. They're not imitating a sine wave. They're not doing any of this wavy stuff. They're pretty much either on or off. That's it. There is no, oh, I'm sort of on. I'm okay. No. There's no halfways. There's bar or no bar.
Well, I can't draw this precise enough to show you that.
So you should have said that right from the beginning, and you should have just pointed out how this is all bullshit anyway. This doesn't work. This will not give you the right answer. It won't give you the pattern. It won't predict it. It's just a pile of crap.
Let me get rid of all of this mess real quick. Get rid of that. Out of the bottom hole, what would you get? You'd get this. A nice spherical pattern coming out of here.
So again, he has the wave center in where the math doesn't do that. Math doesn't say what's the center of the slit and what's the distance from the other center of the slit. That's not where the vectors are going to come from. So he's not going to do the math from those points. So why is he drawing the waves there? That's not where they are in the math.
Might not exactly be the same intensity throughout here, but I can't draw it with the exact right intensity. Up here, this intensity of this portion would be smaller than this portion here, the degree to which it's spreading, but this will help me visualize it. You've got this wave spreading out of the bottom hole. You also have a wave spreading out of the top hole. And now these are going to overlap. Let's draw them both. Boom. Waves overlapping in the same region. You're going to have constructive and destructive interference.
And it's going to be in the wrong place. So it's clearly wrong, so he just keeps doing it. Like I said, even the single slit, you can know it so obviously, right? That's not where the waves have to be. In the single slit, their math is overtly telling you just to measure the distance of the opening. That's all they do. And in this experiment, they're just going to measure the distance of the impediment. They're going to do the cheat math, which is to ignore the openings, the slits, and pretend that all the patterns look the same when all the patterns won't look the same, quite obviously. The small bars will be much smaller. All they'll predict is the envelope size. They won't predict the right pattern, both patterns.
And if you look, remember, these lines represent...
See, you have to understand again, the envelope will be decided by the smallest distance. So if you make the impediment much bigger than the slit width, then the envelope is going to be decided by the small opening size. So that'll tell you the size of the big pattern will be decided by the smallest distance, and the small pattern will be decided by the largest distance.
Peaks. So every time a peak lines up right over a peak, or in the middle, a valley over a valley, every time the wave is exactly in phase when it gets to the same point, these are all constructive points. So right in the middle, you'd get a big bright spot.
Right, and that's why this whole thing, like I said, that's why you get this double bright. It's because that's an illusion. That little center one, see, you draw 2 vectors from these 2 openings. Oh, no, I keep forgetting to use this thing. Draw 2 vectors to the center. You can sort of understand that's a tiny amount of distance, right? I mean, those 2 vectors are the angles are insanely small because it's all happening. They're going to travel meters of distance, and they're going to land within a half millimeter. Their whole life is in this half millimeter. Their whole the whole happening of those two vectors. Those two vectors, if I draw them as straight lines, you could understand, oh, they're still only going to be 1/2 millimeter apart when I make them equidistant. And all the changes in length that take place in here are all going to happen within 1/2 of a millimeter. It's so irrelevant. So this center maxima is nothing. It's so tiny. It's just there. It just fills in the gap. And that's all it does. It just creates extra light so it fools you, so you don't see the real two nodes that are actually going to be created by the experiment. The two nodes start here at the edge of the slits. That's where the nodes start. Okay, and this just fills in the gap between the two separated nodes. The nodes can overlap each other, don't get me wrong. They aren't completely separate, but I'm just saying it fills in that middle part so you don't see them with a little bump in them. You don't see the middle getting darker. The middle would be darker if that wasn't there. All right, yeah, that's enough. That's a good enough way of saying it.
That's kind of weird. Right in between these holes, there'd be a big bright spot. Where else? Well, look at this. Bright. This is constructive.
So it'd be a very small bright spot if it's just made out of the scatter. It's not a huge, it's not going to be that much of a source of light. And the real bright is coming from the fact that some of the light just goes straight through these slits and doesn't get broken. So that ends up in the same one little tiny spot. That's the one that's really filling in the gap.
Constructive, all constructive. They form a line. They get these lines of constructive interference. Same with this line, constructive, constructive, all the way over to here. So on the wall, you'd see multiple bright spots down here.
Right, and they're all in the wrong place mathematically.
These are all constructive because peaks are lining up perfectly. And I'd get another one here. You keep getting these bright spots on the wall. They wouldn't last forever. I mean,
so this is a little gremlin story. Blah, 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 blah. This is their whole gingerbread foundational theory. This is where they invented the gingerbread land and candy land and gremlin land and, hobgoblin land. This is where it all comes from, is this little storytelling they do.
At some point, it'd start to die off. It'd be hard to see. But you'd be getting these bright spots.
Yeah, the light gets tired. When the logical explanation is these are sources, the sources are it's being created by a real mechanical process. And yes, the mechanical process has limitations. Not too many photons hit 15 electrons. Lots of photons hit 4, but not too many hit 15. And that's what you need to make the big bends. You need to hit a lot of electrons to bend a lot.
Continuing on, at some point they're so dim you can't see them. And in the middle, well, wherever, let's see, what's a good point to look at? Wherever a peak lines up with a valley, so this wave's a peak right here, but for the other wave, look at, we're in between the two green lines, so at that point you'll have destructive because the peak is matching up with the valley, and this would be destructive, and this would be destructive.
So again, this isn't what the math predicts, it isn't what the math is, it doesn't illustrate the math, it's completely inconsistent with the math, blah, 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 blah. But this is physics, right? Physics doesn't really care about those kind of facts. So they say that there's all this mathematical precision, we care, blah, blah, blah. You can see where they obviously don't care. It doesn't have to work right. It just has to be somewhere around, and they'll accept it when they want to believe.
So in between here, you get a destructive point. The same is true. In between each of these perfectly constructive points, you get a perfectly destructive point. In between those, it'd be kind of half constructive, half destructive. It would merge into each other.
Yeah, we know that doesn't happen. So he keeps saying it'd be half of something. There's no half in the experiment, okay? There's just none. There's bands of light. They're bands, they're bars, they're blotches, they're whatever you want to call them, but they aren't doing gradually on, gradually off, gradually on, gradually off. That's what he's saying this wave would create, and it doesn't create it. And that's obvious in photons. I mean, it's obvious.
And what you get, sometimes physicists draw a little graph to represent this. You get a bright spot in the middle. This is sort of representing a graph of the intensity, 0, and then another bright spot.
So we know the intensity in the middle is completely being controlled by the fact that, well, I know, you should know, Some of the light isn't bothered and goes straight through. So that means it's going to be brighter in the middle. Some of the light is creating this fake node in the middle, the light that's going this way instead of the light going this way or that way. It's going this way. The two beams are in opposite directions, but that's a tiny bit. It's only a 0.5 millimeter.
Spot, and it goes down to 0 again, another bright spot. They get weaker and weaker as you go out. At some point it's hard to see. Same on this side, 0, bright spot.
So the two nodes are what's creating the big center. Just understand, the nodes don't start until that 0.5 millimeter apart, and then it doesn't start with full bright. It starts with going bright, not full bright.
0, bright.
Well, it only starts with full bright in the one circumstance where you have exactly a perfect number of wavelengths fitting in the distance. So if the surface is precisely 7 wavelengths wide distance, then the two nodes will be pretty close to each other, pretty merged. But that's the unusual circumstance, right? It's a lot easier to be not a full wavelength than it is to be exactly a wavelength.
Spot. This is the classic double slit pattern you'll see on the wall, and it's caused by wave interference.
Okay, it isn't caused by wave interference. It's nail in the coffin. I've provided nail in the coffin evidence that it's not. If you did any thinking about this experiment in any kind of honest way, you would have said, this doesn't make any sense. I mean, why am I putting a wave in the middle of the slit? The middle of the slit's never in the math. Why am I doing this? But you just don't, because you want to believe in Jesus. So you'll look at the toast and you'll see Mary, but she's not there.
In 2 dimensions. And what's the rule for wave interference in 2 dimensions? This is the same rule as the wave interference for 1 dimension. It was this. Remember, for 1 dimension, delta x, the path length difference, had to be 0.
Right, so the path length difference, and what are they going to use when they do the math? The path length difference will be from this surface and this surface, right? I mean, it'll be from this surface and this surface. That's the number they're going to put in their math. So like I said, I mean, it's kind of obvious that's not what you just drew. So why doesn't your math match your drawing? I mean, isn't that one of these kind of easy things to get right, is to draw it the way it's mathematically supposed to be?
Lambda, 2 lambda, 3 lambda, so on, would give us constructive interference. And now if you're paying close attention, you might say, hold on, there was a condition. Remember, this was only true if there was no funny switcheroo business with the back of the speaker. We had to make sure that these 2 sources were in phase to start off with. Is that true of these light waves? It is. In fact, that's why we do it double slit like this. That's why we take 1 wave. We let 1 wave come through here. That way, we break it up into 2 pieces. Why? Because we know if a peak was going into the top hole, well, the same wave was going into the bottom hole. That's also a peak. This is a tricky way, a quick, easy way to make sure your 2 sources coming out of these 2 holes are exactly in phase. You don't have to worry about any phase difference caused by the source. You just have to worry about a phase difference caused by the fact that these waves...
So again, this was this incessant need to compare it to water and sound when clearly light isn't either one of those, and the same rules don't apply, and blah blah blah. And this really is just about a frequency and phase, and so it's just like the polarizing films. I've already been over this, but I mean, come on, it's kind of obvious. As soon as they realize you stick that middle filter in, okay, and all of a sudden you're getting light back, right? You have 2 filters that block all the light, this way, and then you stick a 3rd filter in, you get light back. Doesn't that tell you that you never destroyed anything? It's still there, and now you're getting it back because you've just put it back in phase. And that's all this is about, is putting things back in phase. This is about breaking photons and remaking photons. This doesn't have anything to do with any kind of wooey superpositions or entanglement or destructive anything. There's no destruction here. Energy goes places, and it either comes back into a form you can decipher or it doesn't. Just like you can jam a radio. Does that mean because you jam the radio, the signals don't exist anymore? That there's no energy in them? No, it doesn't mean that. It just means that they're not receivable. You can't decipher them.
Waves are going to travel different distances to different points. And what do I mean by this? What does path length difference mean here? Well, if I look at from this top line, or this top hole, this is basically like our speaker. One source here, but it's light instead of sound.
So again, he keeps doing it. It's like a speaker. It's like this is the center. So he's got these little arrows right in the middle of the two holes, and he knows the math doesn't use that distance. The math won't care about that distance. It won't be relevant. It won't be used.
Waves. From here to the center bright spot, the wave from the top hole had to travel a certain distance. And from the bottom hole to that spot, wave had to travel a certain distance. So
he's just using this vague notion of a certain distance. And we know that distance is almost imperceptibly small because it's 1/2 of a wavelength barrier here, let's say, right? A 0.5. That's a tiny difference in those two lengths of those two lines. So you'd almost can figure out, whatever's happening there is really small. It's not going to make any big pattern. It's going to make an insanely small pattern. The whole pattern is going to be on this wall inside of 1/2 of a millimeter. Everything that drawing can produce, all the variations of those lengths of those lines, are all going to be within 1/2 of a millimeter on the screen. I mean, it's just the basic physics, the real physics.
Basically, this we can call x1, this length x2. And the path length difference would be x1 minus x2. The difference in these, and you can just make it the absolute value if you want, but the size of the difference between these two path lengths. What is that going to be for right in the center? Well, that one's just delta x equals 0, because the waves are traveling the same distance to get to that point.
I know, but they're not going to do it for very much of a spread. So it's the waves that are going towards the outside are the ones that count. They're the ones that are going to cover lots of distance on your screen. They're the ones that are going to count for the pattern.
That makes sense. That's a constructive point because 0 gives you a constructive point when the path length difference is 0.
The real key one is when you draw a straight line. Okay, this is where it really starts. Okay, this is where the pattern really starts. Is when you draw your line straight, okay, and it's only 0.5 from the straight line from this side. So they're only 0.5 away from each other. But that's where the two patterns start. That's where you start. That's the real 0. The real 0 is 0 over here and 0 over here. That's where the two surfaces create their pattern. The two initiating surfaces. Like I said, there's 4 surfaces in the experiment. You just can't deny that. Anyway, moving on. Continuing.
How about the next point? Well, the wave from the bottom has to travel this far. The wave from the top hole has to travel this far. This time they're not traveling the same distance. The wave from the bottom hole is traveling...
Right, so there's no point because it's like I said, he's using the center of the slit as the source, and the math doesn't use the center of the slit as the source. So he's just completely using this fake drawing to give you a fake impression that this stupid analogy works. And it doesn't work. Wave theory fails to explain the experiment. It fails. It fails. It fails.
Farther. How much farther? Well, it's got to be the next one. It's got to be lambda. So this wave is going to be traveling, the bottom wave would travel one wavelength further to get to this point than the wave from the top hole, because that's the next possibility for constructive interference. Note, it's not from here to there that's one wavelength. This is a common misconception. This distance on the wall between constructive points is not one wavelength. The difference in path length that one wave travels to get there compared to the other wave is one wavelength.
Duh. Obviously this magnifies any change in the distance. So the closer I bring the screen, the more imperceptible the pattern will be. But yes, the length of the lines will become more and more consistent with an actual wavelength. But yes, the pattern gets bigger and bigger as I go further away. Obviously, is proportional to the wavelength, but isn't going to be the wavelength in terms of numbers. And it really has to do with pi. It has to do with the fact that if you put this pattern on an equidistant screen, all you need to understand is how the circumference grows by comparison to the radius in a circle. So, I mean, the circumference gets bigger as the radius, as in comparison to the radius with the size of the circle.
And I bet you can guess the next one. The next one, delta x, would just be 2 wavelength, and you can keep going. How about the destructive points? Shoot, you know how to do that. These are going to be the half wavelengths, lambda over 2. This one's going to be 3 lambda over 2. And so on. And down here, what would you get? Well,
and again, it's just this whole idea that you won't get these numbers when you project on a flat screen, because the numbers are getting distorted by the fact that you're stretching, you're widening, you're changing the proportions. You're going to make this distance change with distance. So the further away you go from the center, the more distortion you're going to have. So your math won't work for that reason also.
You got rid of the absolute value sign and you wanted to, you could start talking about this delta x would be negative 1 lambda. This one would be negative 2 lambda, and so on.
Yeah, there's really two patterns. I mean, there's the patterns from the sources going that way, and then the patterns going that way. And that's how you really have to understand it. There's two directions the scatter can take. The scatter can go this way, or the scatter can go that way. That's the simple way to understand it. But anyway, I think we've done our job here, and
so you could have negative values if you wanted to denote the fact that they might be lower or higher.
I mean, it is kind of amazing that, I really have dissected it. I've come up with the proper answer to this grandest mystery of all mysteries in quantum physics, blah, blah, blah. I mean, I could give you the quotes, the hypey quotes for 100 years about this experiment and how this is the thing and blah, 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 blah. And right here, I've shown you, I've pulled the curtain. You can see the wizard. You can see the levers. There is no Mr. Oz, okay? It just doesn't exist. All right, the whole thing has been a game of mirrors, and a trick, okay? A little simple puzzle that the brilliant physicists were just so busy, petting each other and saying, "Oh, I love your little gremlin theory. Oh, that inventing hobgoblins was incredible. Wow." They're so up each other's ass that they never took enough time to say, this doesn't make any... We're talking crap here. This is silly. And it was overtly silly. I mean, this isn't even, this mistake is so glaringly stupid, all right? And that's it. It's so stupid. And there's just going to be no excuse. They're aren't going to be able to explain, well, how did we make such a stupid mistake? And the only way they made it is because they're fundamentally religious kooks. And that's all. Human beings are I guess you just can't beat it out of them. They just want it. They're so desperate to live in a special verse. A little yellow bussiverse. Ugh. Ugh. Alright, so as stated, all I can do is reason with you people. If you're unreasonable, you're unreasonable. Not a damn thing. Not much I can do about that. So, I mean, I've made it as simple as I can. I've pointed it out. I've illustrated it. I've beat it to death. I've played you video after video of just overt deceptions. It's time to concede. Their game is over. Yeah. All right. So, till next time and such.